So today in magnetic resonance community, there are lots of simulators and there are lots of free uh, open source softwares. Some are commercialized, but out of the free open source softwares, some are on a paid platform like MATLAB and Mathematica, and some are in free platform like C, Python. So there are lots of softwares. So some of us are confused what to choose. So here is PyOR, another simulator to increase this confusion of choosing. Yes. So PyOR. Yes. So PyOR stands for Python on Resonance, as you can see the logo of PyOR. And it is a versatile NMR simulator for liquid and solid simulations based on Python. So the concept of PyOR began when my supervisor Daniel said, let's do it semi-quantum mechanically. After we made the first draft of this paper of multimode measures thermally polarized nuclear spin. As because before that we were doing block equations to simulate NMR measures, and since we started working on coupled spin system, block equation is not so useful, so we need to do semi-quantum mechanically the simulations. And so I first of all looked into commercial available simulators. Where is there any softwares which already implemented radiation damping and measures? But unfortunately, I did not saw it. So I need to make my own software to do my simulations. So it became my hobby since 2024 to program PyOR for nonlinear dynamics. And it's still a baby compared to other softwares like Gamma, Spin Evolution, Spinach, Simpson, and Spin Dynamica. I have released the beta version of PyOR on August 2024, and it is available in my GitHub. And my first version of PyOR I released this year in April. So the motto of PyOR is everybody can simulate magnetic resonance. And some of you may ask, what is the purpose of PyOR? There are lots of softwares. So its main purpose is to simulate nonlinear NMR, which is radiation damping and measures. And it will be an interesting package for beginners who are curious to know what is spin physics of NMR from any background like physics, chemistry, or biology, and to learn NMR. And you will see today, PyOR is a good choice for teaching in classroom. And PyOR is coded such a way that the user can easily understand the spin physics from the code. And also users are welcome to modify the source code. At the moment, PyOR is not a quantitative software because you cannot, it's not having the capability to like fit a real life experiment. But it is more qualitative to understand how an NMR experiment works. So brief features of PyOR, you can generate all the spin operators of a given system with any number of spin. Any number of spin means I tested for 6 spins with any quantum number. And you can solve Liouville equation in Hilbert space or in Liouville space with relaxation in both. So either you can you can propagate the density matrix using unitary propagator, or you can treat Liouville equation as a set of differential equation and you can solve it. I have implemented the Redfield master equation, so you can have phenomenological dipolar relaxation and random field fluctuation in Redfield, and in Lindblad, I have implemented dipolar relaxation. You can create Hamiltonians as you want. There are also pre-written Hamiltonians inside PyOR. And PyOR is purely made from Python package like NumPy and SciPy and Matplotlib. Now, a brief overview of simulation in PyOR. Like first, you want to define a spin system, and you want to define what are the interactions between the spins, and you want to choose a propagation space and a master equation. Then you can define the parameters like chemical shift, coupling, the relaxation parameters. Then you can generate an Hamiltonian. You can initialize the density matrix. Then you can evolve the density matrix. You can compute the expectation value, and you can finally plot FID and spectrum. So here, this figure shows a structure of, or the structure of PyOR. So there are, you can see lots of boxes. They are nothing but modules of PyOR. Modules, I mean, they are some Python file. And the color, you can see blue and red. So the blue are the Python files which contain classes. And these red boxes are containing modules with functions. So you can see different arrows with different color. So here, this blue is the input to the PyOR. So we input the spin list and the parameters. And you can see the green arrows. They are internal. The classes are sharing information internally, so user cannot access it. For example, in Hilbert space, the user don't need to think about relaxation. It will be automatically taken care by the program. But in if you come to alluvial space, then you can generate all the relaxation superoperators. You can access them. And you can also generate product operator basis. Then finally, you can evolve the system and you get the density matrix as a function of time. From there, you can calculate the expectation value. You can directly plot the FID, or you can use this module which for like Fourier transform, and you can plot the spectrum. So how to start PyOR simulation? So first of all, you want to download two folders from this GitHub of PyOR. One is a source doc, which contain all the Python files. And to begin with, there is a folder called example, where you will have lots of Jupyter notebook files, examples. Then you need to install Anaconda, a Python distribution. Then most of them will know about PS Visual Studio Code. You want to install that. And you also want to install this IPyMPL using pip install IPyMPL for interactive plotting in PyOR. Now, we all have some problems to solve in NMR. And for the beginners, if they're looking for some problems, I suggest this book, where you can use this book and try to simulate the different problems using PyOR. Now, I will show two examples in this talk. So first example is a simple pulse acquisition experiment, and second one will be an NOE. So let's start with the pulse acquisition experiment. So before, this in Python, we can install the package like pip install. Like most of the the programs use pip install to install the package. But in Python, I don't do this kind of, I don't prefer to install a software, because I'm expecting the user to modify the source code according to that problem. So what you will do, you will download the PyOR source doc folder, and you define a path. Then you use this Python module, and you can use this command to append this path. So when you run PyOR program, PyOR script using VS Studio Code, the Python will automatically look into the source code and will do the simulation. Now, when you write a simulation script, you want to first define the path to the source codes, and now you want to import different modules. So PyOR has many modules, and these first four modules I have mentioned in this red box are the pillars of PyOR. So if you look this module, PyOR quantum system, it is nothing but a Python file which contain a class called quantum system. And this is the first pillar of PyOR, which generate spin operators, quantum states. Now, next, another important module is PyOR quantum object, where there is a class defined called quantum object, which we will see later what it can do. And similarly, we have quantum library module. We'll see what it can do. It is very powerful module. And we have a basis module where it can generate product operator basis. Then there are modules to generate Hamiltonian, like a J-coupling Hamiltonian, dipolar Hamiltonian, and you can look into this file to see what all Hamiltonians are defined inside PyOR. Next, there is modules for generating equilibrium density metrics to make pulses, then to evolve and to plot and to do signal processing. There are other modules which I did not mention, but because these are the major modules which we'll use in this discussion. Now, first, we are going to define the spin system. So we already have two spin, A and B. They are J-coupled. And we define first a spin list. So we have first spin A, which is proton, and second spin B is still proton. You can define another list with single spin or with like proton or deuterium, anything you can define here. Now this spin list is argument of quantum system class, which create an object called QS. Then later you will initialize. So after initializing, executing this command, it will generate all the spin operators. Now, after initializing PyOR create all the angular momentum spin operators. These operators created are objects, they're quantum objects. I'll explain what it is. So we have first three components of angular momentum operator, X, Y, Z. So for the whole system, you can access the spin A's X component and B's X component. And for subsystem, like considering the operator only for the single spin, you can use AX sub, which will give you the X operator of the subsystem. Similarly, you can you can access the spin operators for X and Y, Y and Z spin operators. Then you can also create the raising and lowering angular moment operators. So you can access the raising of A and B and its sub operators, also for lowering operator. Now, what is a quantum object? So any operator state of PyOR is a quantum object. Before introducing this function, you can also generate your own quantum state and operators. So you can use the PyOR quantum object module which contain quantum object class. So if you want to create a state 1, 0 or 0, 1, some basis state, you can use this line and you can create two ket states. Or if you want to create your own spin operators, you can do that. You just want to define what is the matrix form inside this class. So here you can create Sx, Sy, Sz, your own. And also you can create identity operator. Now, each quantum object has an attribute and methods. So if you look the attributes, so if you take the quantum object ket, and if you write dot matrix, it will give you the matrix form. If you type dot type, it will give you what kind of object it is. It's a state or an operator. Now you can also see by dot data type, you can see what is it. Like it's now currently by default, it is complex number. And you can also get the shape of the object. So for Sx, you'll see 2 by 2 matrix. And if you want a NumPy array, then you can write dot data. Then you have different methods. So you create state. Now you want to make some operations on this state. For example, you want to rotate the ket state. So you can use dot rotate 180 degree about x-axis. It will create a new object called ket3. You can multiply two objects. You can add two objects. By using this, you can create your own Hamiltonian. So there are predefined Hamiltonians in PyOR, but if you want to create your own Hamiltonian, you can just define the spin operators and you can create a Hamiltonian from that. Then you can make other properties like adjoint. You can take conjugate. You can take transpose. So if you write transpose, you can take the object, take its transpose. If you want to see the matrix, you can write dot matrix. It will give you the matrix form. And other methods are, you can take the trace, you can find the norm. If you want to calculate the exponential of an operator, you can use dot expm. If you want to check an operator is Hermitian or not, you can use dot Hermitian. If you want to check if two operators can commute, you can use dot commute. And you can do tensor product. You can do outer product. You can do inner product, and also you can even normalize an operator. Now coming back to our two-spin problem, so we created spin operators. So if you want to check the matrix form of particle A, its X component, you just type dot matrix. And similarly for other operators. So if you look here, this is the X component of spin operator first particle. It's in its subsystem. Now, next, after defining the spin system, you want to define the parameters. So PyOR you can work in Hilbert space, Liouville space, or you can solve Schrodinger equation. So currently, we are going to use Hilbert space for this problem. And I'm going to use Redfield master equation. You can either use Redfield or Lindblad. So here in this problem, we use Redfield master equation. Now you can define the basis of operator. By default, it is Seaman basis. If you are working with, if you want to work with singlet triplet, you can use singlet triplet. Then later, like if you want to change the basis into some to the eigen basis of the Hamiltonian, you can use this line. It is still under testing, but it is implemented. I have tested for a few problems, which is in example folder. It looks it works, but so you can also work with eigenbasis of your Hamiltonian. Now you define the field in Tesla. Then you can define the offset frequency of spin A and B in Hertz. Then you can define your J coupling between A and B, which is 5 Hertz. And you can define the individual initial and final spin temperature of the spins. And now you can choose the relaxation process. So here I'm choosing phenomenological relaxation. There is random field fluctuation, dipolar, homonuclear, and heteronuclear implemented. To see what are the possible value for this R process, relaxation process, you can look into this PyOR relaxation module. You can see what kind of relaxations you can use. So here it is phenomenological, and you can define the transverse and longitudinal relaxation rate here using qs.r1 and qs.r2. Then you finally use this command qs update, which will update all the parameters you just gave, and it will share with other modules. Now we want to generate Hamiltonian. So we want to call the Hamiltonian class. You want to give the object QS into it as input parameter. This is how it understands, it gives, this is how our defined parameters are shared with Hamiltonian class. So you can create a Seaman Hamiltonian in lab frame or rotating frame. If you want to see what is its matrix form, you can use dot matrix, and if you want to see the matrix in Hertz, you can use inverse 2 pi, which will divide the matrix by 2 pi, so that you can see the matrix in Hertz. If you want to round the matrix elements, you can use dot round. So it will round to 2 decimals here. Similarly, you can create a J coupling Hamiltonian, and you can use the matrix form. Now, next, we want to initialize our density matrix. So we can use this module, this class density matrix. You give the object QS and ham, which you created in the previous slide. Then either you can define your own density matrix, initial and final density matrix, or you can use equilibrium density matrix. So if you want to use equilibrium density matrix, you can make it true. And you can use high temperature approximation if it is true. Then you can call this method equilibrium density matrix, which take the input initial spin temperature and high temperature approximation. It will create the initial density matrix. And if you want to see its matrix form, you can just write dot matrix. It will give the matrix form. Similarly, for final density matrix, and you can also create your own initial density matrix. Now, some interesting function in PyOR, which is this function, which you can split, you can decompose the density matrix in some product operator basis, which is inspired from spin dynamica. So you can use the class basis. You give the object QS as its input. Currently, I'm going to use an example of shift basis. So you're going to create 16 product operators in shift basis. So you take argument sorting. So you can sort the coherence from negative to positive. Then you can create some index. That means you can call the operators with some number like 1, 2, 3, 4, which is by default it is false. Then you can normalize the operators. Now this function will return 3 things. So here it contains a list of quantum objects which are the product operators. Then it gives the coherence order, and it will give a dictionary of product operators. So it will give you the coherence order. So we are sorting from negative to positive. And in the dictionary, it will give the 16 product operators, I minus 1, I minus 2, I minus 1, IZ2, 16 product operators. Now, if you want to call the operators by this dictionary, you can use string to matrix function. It will create another list of objects, and you can call your product operator by their name. And to see matrix form, you can type dot matrix. So now you can use this function defined in density matrix class. Density matrix component, you give the input, the density matrix, the product operator basis, and the dictionary. It will split the density matrix into the product operator basis. And other basis which is implemented is spherical basis. So there is a general spherical tensor basis for any spin, any number of spin, and with any quantum number. And there are also special cases for only spin half. You can use this second function to make for spin half spherical tensors, and also Cartesian and Seaman for spin half case. Now if you want to make some pulse, you can use this module, hard pulse, and you can define how much you want to flip the spins. So you can say, I want to flip both spin 90 degree. Then you can use this function rotate pulse. You give the initial density matrix, the flip angle, and about which operator you want to rotate the density matrix. So you can use that, and it will rotate the density matrix. Now, if you want to, so the problem is if you make the matrix form, sometimes you will see some numbers which are very small, like 10 raised to minus 15, minus 16. So if you want to remove all that small values and make all the small value into 0, you can define a tolerance value by dot tolerance, where it will make all the values less than 10 raised to minus 5 into 0. So you can define your tolerance here. Now, after rotation, you can use the density matrix component function in the same way we used in the last slide. You can decompose the density matrix into the product operator basis. Now, to evolve, you can define the dwell time. You can define the acquisition time, and you can choose the method to solve this problem. So for this problem, we are going to use ODE solver. Means we are going to use a solver to solve Liouville equation as a differential equation, because we are going to use relaxation. If there is no relaxation, you can use unitary propagator as a propagation method. There are other methods defined, unitary propagator with time dependence, Hamiltonian, and you can solve Lindblad using ODE solver Lindblad. Then if you want to solve shaped pulse, you can use this option. Then there is relaxation in Liouville space. We'll use this to have exponential propagation with a relaxation superoperator. For this is the case of Redfield, and this is for Lindblad. And all possible options you can check in PyOR evolution module. Now you call the evolution class, you give the input quantum system and Hamiltonian. Now you can evolve the system using this method, which take the initial density metric, the final density matrix, and the Hamiltonian. There are other arguments depending upon the problem we will add here. For example, if you want to use time-dependent Hamiltonian, we can also give an array of Hamiltonians in this as argument to this function. And you can use the standard Python function to compute the time of evolution. Now, so this function, which will return all the time points and also the density matrix as function of time. Now we want to find the expectation value, so we can use the expectation function. So we define what we want to detect. So we want to detect the transverse magnetization and the Z magnetization, and you can compute the transverse magnetization from using this function. And if you want to Fourier transform, we use the function defined in signal processing module. You define, you give the argument as your your magnetization, and your 1 by dt, the resolution in frequency domain. And this number means you're padding zeros 5 times the size of the array, which is of this transverse magnetization. Now, Python in PyOR, you have many functions to make plotting, which are defined inside this class plotting. And you call this class. Now you can define your figure size, your font size, the limit in X and Y, and you're going to use one function called just plotting with a span selector. That means you can measure this x-axis here by using your cursor, and it will say what is the difference. So here it is 5 hertz, which is mentioned here. And to this function, you give the x-axis, which is frequency, the y-axis spectrum, and you can give the label of x-axis and the label of y-axis and the color of plotting. Now we go to the second example, which is NOE, two-spin system. So we have 2 spins. They will relax due to dipolar field. So I am skipping this initializing lines where you define the spin list. It's the same. Now I'm mentioning what you will add new or some changes you are going to make. So instead of using Hilbert space, we are going to use Liouville space to solve this problem. And we are going to use Redfield master equation. Now you want to define the couplings, which spins are coupled dipolar. So you are saying A and B are coupled by dipolar field. Now you can choose a relaxation process. Since we are doing dipolar, we are also, and both spins I defined as protons. So we can use autocorrelate dipolar homonuclear variable for this R process. Then you can define the correlation time, which is 10 picosecond. And you can define the dipolar coupling, which is 30 kilohertz. Now you can create the Hamiltonian as before. You can create Seaman Hamiltonian, you can create a J coupling Hamiltonian. Now comes the use of the module quantum library, because you want to make, to solve the Liouville equation, you want to create the commutation superoperator. So we use the methods defined in this class, quantum library. So before, so we, in Liouville space, we vectorize the density matrix, and how we vectorize the density matrix, either by row or column, the definition of the commutation superoperator will change. So in PyOR, you can choose how to vectorize the density matrix. So if you write C, it will vectorize by column, by row. If you write F, it will vectorize by column, and the corresponding commutation superoperator will be created. So to create the commutation superoperator, you give the Hamiltonian you just created as argument, and it will create the commutation superoperator, which you can see as a matrix by typing dot matrix. Now, some functionalities of this quantum library. So you can create some states by saying basis ket. You can say it's a two-dimensional column vector with an element 1 at its first point, which is here. And you can create a second, for this typo, it should be 2. So you can create another basis by typing at second place you want to create 1. So you create the basis of a system, and you can create some wave functions as you want. I forgot to mention, actually, this quantum library and quantum object modules, they're actually inspired by a software called Qtip. So this is an inspiration of this package. And in quantum library, I have defined outer product. And if you can create, you can vectorize the density matrix using this. You can you can build the density matrix from the column vector using this function. So if you give the vector you want to make as a density matrix, you can define the column vector, and you can say the shape of the matrix. It will give back you the density matrix. So here, using this outer product, we created a density matrix. You can vectorize using this function. And if you want to go back to the density matrix, you can use this function vector to density matrix to get back the density matrix back. There are many functions defined in this module, very useful, like inner product, outer product, lots of functions are defined. I ask you can go and check this module, and also there are examples to show its capabilities in the example folder. Now back to NOE. So if we choose the space is Liouville space, then the density matrix will automatically give you vectorized density operator. You don't want to think about making it vectorize again. No, it will automatically will vectorize the density matrix, and you can directly use that. Now you're going to make a 180-degree pulse on the second spin and not touching the first spin. And you can use you can rotate the density matrix using the function we used previously. So here also, you don't want to bother, okay, I mean, Liouville space, should I do something else? No, it will automatically know which space and what to do. And now you want to create the relaxation superoperator. So if you see in the previous example, you did not show any relaxation operators, because it is done internally. So PyOR will internally compute the relaxation. So you don't want to bother about it. But in alluvial space, you can create the relaxation superoperator. For that, you want to call the class relaxation process. And you can use the function relaxation, and you will get a quantum object, which will be the relaxation superoperator, which you can visualize by dot matrix. So this is the relaxation superoperator. Now you want to evolve. So you're going to evolve exponentially. So you can use relaxation variable to as a method of it will propagate exponentially with relaxation into it. Now you can evolve using the function we used in the previous. So now we have an additional argument, which is the relaxation superoperator. And as we see last time, you can define the detection operator. So we are going to detect the set magnetization of both spin. Now you can find the expectation value using this function. And you're going to plot. So here is the different functions to make plotting. It's plotting multi. That means you can plot more than one function in the plot. So you give a list of two time points. You give the expectation value, the set component of first spin and the second spin, which you compute previously, and the X label, which is time, and the set label, which is MZ. You can plot both in different color, green and blue, and you can see the evolution of MZ in this plot. Now I will show some features of PyOR. It will be very brief, but to show the capabilities of PyOR. So one of its unique feature is you can do radiation damping, a semi-quantum way. So it will compute the dipolar field by calculating the expectation value of the transverse magnetization, and the radiation dynamic field is proportional to this transverse component with a constant, which is the gain, which will be the circuit your probe parameter, which is G. And we have a phase, and this phase is nothing but the phase difference between voltage and current. So we have a single spin system, and I'm not repeating the parameters which I showed in the beginning. So this is the additional parameters. If you want to use radiation damping, you can say QS dot R damping is true. You can define this G constant here for each spin. So here we have only one spin. So you can define it for the spin A. And you can define this phase, this psi, which is at 0. And we are going to see a 180 degree, a near 180 degree flipping, and see what will be our FID. So we are going to, yes. So if you have already done some 180 degree pulse on water signal, you can see the transverse component is not exponential, but a hyperbolic secant. And so when you simulate this problem, using a different plotting function, which is plotting twin span selector. So span selector means you can measure the distance of x-axis, and twin means you can have two different y-axis. So you can plot the signal, which is the hyperbolic secant after the simulation, and you can also plot the MZ trajectory in the same plot. I have never made any example for this. It will be soon because we are writing a paper on PyOR. So we will see more details in this paper. Now, one of the feature for measure people who do measures, they want to analyze their measure FID. So here I have a module called PyOR Measure Data Analyzer. You can import this class Measure Data Analyzer, and you can import your data, which is a simulated data or a real experiment data. you can define its path, and you can tell what is the dwell time. And if it is simulation, you want to mention simulation is true. And you can get this plot. So the beauty of this plot is, so here it shows the FID. So in Maser experiments, we can see that the frequency component in the FID will change with time. So if you want to analyze what is the frequency component in the selected region, it will Fourier transform this selected region, and you can get the corresponding spectra for that. And the same way here, so these both are active plots. If you touch it, you can make some change. Now, if you want to see what is the corresponding FID for this given peak, you just select it, and you will get the corresponding FID for that particular frequency. So the blue will be the total FID, and the red will be the FID corresponding to the peak you pick. Now, next, you can do shaped pulse simulation. So this example, which is detailedly mentioned in the example folder, you want to simulate shaped pulse with radiation damping. So additionally, you want to define, so I'm using the shaped pulse from Bruker. So this is an example of RSNOP. So you want to define the path to RSNOP file. You will define the pulse length. You can define the angle of rotation, and you will use the Hamiltonian class, and you will use this this function shaped pulse Bruker. You import these variables you defined, and you will get the time point, amplitude, and phase. So in PyOR, we can solve, as I mentioned, exponentially propagating, or you can solve differential equation. So you want to give a continuous points for amplitude and phase if you are in Hilbert space. So you can use interpolation function defined in the Hamiltonian class. So that if you give this discrete amplitude and phase, you will get a continuous amplitude and phase, which will be used by the solver to solve the alluvial equation. The detailed example is in example folder. Now you want to evolve. So you define the evolution class. Now you want to define shaped pulse. So I'm using Bruker files. You want to define a shape function, which is Bruker, and the B1 will be I amplitude, and you will define the phase and the frequency of RF you can mention, and you define the acquisition time. You have 1,000 points, and you can calculate the dwell time. And you are propagating with the method ODE solver shaped pulse. So, and now you are going to plot a block sphere. You can use plotting sphere where you give mx the expectation value of x, y, z. You want to give the equilibrium density matrix or the final state, which makes the size of this, the diameter, the radius of this sphere. And you can plot this function, the evolution of mx, my, mz, and you can see we define 90 degree, but due to the presence of radiation damping, we can see that it did not reach 90 degree by using RSNOP. Now, the final example is I also implemented solid state. It is still under testing. Though I implemented, I want to see if there is any bugs inside. So this is an example of CSA, powder averaging. So here you can use the function defined in the Hamiltonian class, the principal axis frame CSA tensor you can create using this. So you want to define the isotropic, anisotropic, and the symmetry you can define, which will create the principal axis tensor. You can see its matrix form by dot matrix. Now, to get the crystal orientations, you can define your own alpha, beta, gamma, and their weights. but I have made some example files from Simpson, which is defined in this module. And by using this load crystalline CSV, you can load that orientations, and you can make these variables alpha, beta, gamma, and weight from that, or you can define your own. Now you evolve by defining the dwell time acquisition time, and you're going to propagate using unitary propagator. So you define that. Now use the evolution function to evolve. So yes. Yes, and now this is a CSA, so it's a spin field interaction. So you can define the variable A is A, which corresponds to the spin A, and this is a field. You are going to use powder spectrum function define the Hamiltonian. Here you want to give the evolution class, which give the information of which defined in the evolution class, and you give the initial density matrix, the final density matrix, the spin A, then the principal axis tensor. Then this is nothing. If it is a quadrupole, you will be mentioning this will be spin B. Then you are saying it's a spin field interaction. If it is quadrupole, if it is dipolar, you will mention spin here. And you can choose the elements of this of the Hamiltonian by writing all, if you want to consider all the elements, or like only the secular, you can write secular. You give gamma, beta, alpha, the angles, and you're saying, okay, you want to weight it, it's true, and you will give the weight, and you can plot the powder spectra of yes, for CSA. Now the conclusions. So PyOR is a baby. It's still developing. There will be lots of bugs, and I'm not a very big expert in because I do mazes, not NMR like others. So maybe I overlooked something. So there can be mistakes I have made. So if you find any mistakes and you have any suggestions, you can write it to me. And in future, my dream is I want to implement various hyperpolarization techniques, also some atomic magnetometry and centers, and I would like to optimize this software. Currently, there is parallelization when you calculate powder average. That's all. Maybe in future, I want to see where all I can use optimization. And we are writing a paper. So after publishing the paper, I would like some contributors. They can develop PyOR according to their problems. And so the documentation of PyOR, you can get it from this link. Probably I need to make it much better. Then you can download the PyOR and examples from my GitHub, and also from Zenodo, which will be stable versions of PyOR. And this probably I will update PyOR with testing. So some things may not work, but this is after testing. I am writing some tutorial in Marcus, Magnetic Resonance, Quantum Information, Science and Education. This is their LinkedIn page and their official website, where you can see not just simulations of PyOR, but PyOR simulations made by others like Hinton Stern. You can, it's a beautiful website, informative. You can check this. You can write it to me in my unofficial email address, which is vineethfrancis.physics. Yes, and I acknowledge Daniel and ANR for supporting this project. And this PyOR is dedicated to my hero of NMR, which is John Jenier. I never met him, but yes, he passed away. And also to the Gaviri, which is the soul and catalyst of PyOR. Thanks.
Thank you so much, Vineeth. That was a great and insightful talk. So we are ready to take any questions. Audience, please feel free to write your questions in the Q&A chat box. We already have few questions here. So I'm going to read the questions aloud, Vineeth, and then you can answer accordingly, if that's okay. I'll try to go very slow. So our first question is from Alex Bolden. He asks, will this work with Magris 2000 software files? They are .mr2 files.
So I don't know what is that file. Is it for some shaped pulse?
Maybe I can try to.
So currently, if it is for shaped pulse, it's only supporting Bruker shaped pulse files.
Okay. I don't know. I'm just going to let Alex talk if that answered his question.
Okay.
Alex, you can talk if Vineeth answered your question correctly.
Hello.
Yeah. We can hear you. Sorry. Yeah, go ahead.
I can hear.
Yeah, great. Thank you, first of all, for the great presentation. It was very nice to see traction in the NMR world and the computational physics world colliding together. And for all your efforts, it's great to see people working on this. Don't worry about the .mr2 files. It's an experimental setup, not Bruker, as you mentioned yourself correctly. So I was just firing a question before I finished listening to your talk, so a bit too early there. But my second question before Tamari, you read it out. It was about on the quadrupolar spin systems. Like I specifically am very interested in quadrupolar antiferromagnets as a solid crystals. And your talk was very nice, and I'll definitely be cloning your GitHub and getting to know it.
Yes. So I have an example of quadrupole. And the point is, I'm not a solid state guy, so I just read book and I code. So maybe I make a mistake. But the good thing is, if you find the mistake, you can correct the program yourself and you can run it. So you can modify the source code according to your needs, actually. So these Hamiltonians are actually defined in the class, in the module Hamiltonian. So you can see the coding part, and you can change anything if you want.
Thank you.
Okay, I think that answers Alex's question. We then have Malcolm. Malcolm raised his hand, so we'll allow him to talk. Malcolm, please go ahead and ask your questions. I already see you have asked Vineeth about, I'm interested to hear about your definitions of thermal equilibrium and the Lindbladian. So, yeah.
So I used actually one of Malcolm's paper to code this Lindblad master equation. So it is from one of your paper. I have implemented this Lindblad. So
can I speak?
Yes, please go ahead.
Hear me?
Yeah.
Sorry, the interface is not very clear as to. Anyway, okay. So as you know, to define the thermal equilibrium state, you have to define the temperature, and then you also have to define the lab frame Hamiltonian.
Okay.
So does PyOR let you do that with
yes,
any Hamiltonian
you can.
want and so on?
Yes, so it's a yes. You can define the temperature. I did not.
What about the Hamiltonian? I didn't, from your demonstrations, it wasn't very clear to me.
Okay.
Maybe it's just I'm unfamiliar with the syntax, but it's not very clear to me when you define a certain temperature or something, what it's actually doing. Is it, which Hamiltonian is it then using to calculate the thermal equilibrium?
Okay, so probably I don't do anything with the Hamiltonian, but when I calculate the spectral density function, I use the e raised to Hamiltonian by kBT. I use to compute the spectral density. So the temperature is introduced into the simulation by the spectral density function.
Right. So again, yeah, maybe because you have to define some lab frame Hamiltonian. Is that including the Larmor frequencies of the different nuclei, for example?
Yes. So these frequencies are in the lab frame.
Yeah, and where are they defined then? Is the program using some defaults for that?
Yes. So when we define the parameters here, it know what is the field, what are the frequencies, and it will, to get the frequencies of exact spin, it will combine these two information and will compute the exact lab frequencies, and which the functions know internally. So I create this quantum system, and these informations are saved in the quantum system as attributes. And when we pass this quantum system, all this information is shared with Hamiltonian and also the density metrics. So it knows all this information internally. So we do, yes. So when we define the parameters, it takes it automatically.
I see. So just for the sake of argument,
okay.
Suppose one was interested in. Okay, I know that you're not that familiar with solid state NMR, but let's just imagine a situation where you just have a very large quadrupolar interaction.
Okay.
So maybe you don't even have a Zeeman Hamiltonian. So this would be like NQR.
Yes, I mean, yes.
So then the Hamiltonian itself is not defined by a Larmor frequency. It's or a static field. It's a large quadrupole Hamiltonian.
Okay.
So can the routine then calculate thermal equilibrium with respect to that?
No. So the relaxation, I don't think it is possible right now.
Okay, I get it. Yeah. But it's a fantastic achievement, I think, so far. The software, to get such functionality, a bit spin dynamic alike at least, or using Python. It's well done. Great achievement. Thank you.
Thanks.
Thank you, Malcolm. And I do see your suggestion to us. So I believe this is definitely due to security reasons, but we are going to take your suggestion into account and look into it as to what we can do so that people can see other attendees as well. Sorry about that.
Okay, thank you.
Thank you. We have another question from Sohail, and they're asking, thank you for sharing this beautiful work, Vineeth. I have a very simple question. Number one, what is your limit on the number of spins you can simulate for?
Okay.
Maybe you can answer this first and I can read out the other questions after.
So technically, if your computer allows, you can go with many more spins. I have tested 6 spin for ethanol. I made spectra of ethanol. So it also depends upon your computer. So I have like 64 GB RAM, so it can maybe make more big matrices. But you can also work with Hilbert space with the relaxation. So you may not go to if you want relaxation, you don't want to go to Liouville space and make a bigger matrices. It's not required. So probably you can. I'm not sure. We want to test that. At least I tested for 6 speed system.
Okay, and for question number 2, have you considered simulating including B1 field inhomogeneities?
Okay, B1 field is is possible. There is a function, I don't remember its name, but if you want to simulate B1 field, it is possible. In homogeneity, it depends upon the spins, so it is also possible, yes.